Anybody use transects? Oh, interesting. How about random allocation or systematic allocation? Nobody. Okay, well this is going to address some of those questions. Which is more precise among those various survey designs? So to test various choices, we constructed simulated populations which were clustered and then sampled with a computer 10,000 times to test the performance of various combinations of those survey designs. Now the problem with clustering in sampling in clustered populations is they tend to cluster, which makes the sample variances wider. It's easy to fall in areas of very high low density or very low density, and so the overall variances are greater when populations are clustered. So we answer the following 4 questions. Which is more precise, random or systematic sampling? Which is better in clustered populations? Again, long, thin transects or square quadrats. If systematic sampling is more precise, why is it not always used? And can we better estimate confidence intervals for systematic surveys? What methods might be available? So this topic has been ongoing since about the 30s, starting in Scandinavia, and we continue that stuff. There's a lot to think about. So we randomly generated spatial point populations inside a 1 kilometer square survey study region. Initially, there was we have 6 populations to consider: a perfectly random population, one where we synthetically just created patchiness in the suitable habitat but distributed our organisms uniformly across each patch. We have a population which only has clustering, like if you might have a parent plant and seeds that disperse around it. And then 2 populations where you combine patchiness of habitat with clustering within the habitat. And these lower patches have much lower density than the upper ones in these 2 cases. So considering those populations, how does this sampling occur? Well, what we do is, for random sampling, this whole population can be divided into 20,000 1/50 transects, which is the first sample plot we consider here. And so for random sample, you just randomly choose 100 of those 1/50 transects from your sample frame with replacement, so there's no repeats. Unique locations are chosen. With systematic sampling, as following the standard approach, divide up the study region into squares where you will assign 1 transect per square, call them grid blocks. And for this particular systematic design called One Starter Line, you first choose a random location for that transect within the grid block and then use the same position in the other 99. So standard random and systematic sample design. In order to estimate density, we just take the 100 density measurements because the computer knows the count inside each transect, divide by the 50 meters of search area. That gives us 100 density measurements from each survey. To estimate density, you just take the sample mean, the regular mean of 100 density measures to get the estimate from that survey of population size. But what we can do with a simulation is run these surveys 10,000 times in order to assess their performance. And we assess the performance based on 2 measures of performance: their accuracy and their precision. So by accuracy, we mean the closeness of the mean of 10,000 repeated surveys to the true population density that we know without error because we created them. So lack of bias is the same as accuracy. It's the closeness of the mean of 10,000 repeated surveys. Precision is defined by the spread of sample values about the mean. Let me show you what the outcomes were. So once again, we have our 6 populations, and we'll look at 30 more in just a second, but these are the initial 6. Then for random and systematic sampling, you get a mean value for each, and the spread of 10,000 repeated sample means based on 10,000 reruns of each survey design, random and systematic, in each of the 6 populations. So it's a simple, direct way to test the performance of each survey design. And it all depends on how close these population distributions are to real ones that determine the value of this exercise. Anyways, regarding accuracy or lack of bias, it turns out that random and systematic designs are both equally unbiased. So if this number is 100%, that's perfect agreement between the mean of 10,000 and the actual true known density. But you can see that these numbers are very close to 100% and equally so for random or systematic sampling. So that's already a good start. We know that random and systematic designs are both equally unbiased. So the way to determine which is the better design, to give you the better information about your study region, is based on precision alone. That's the only thing we need to consider further because it's the only difference between random and systematic. So looking back here again, we see that with a perfectly random population, there's no difference in the precision. Actually, it turns out systematic is a bit less precise, and I don't know why. But they're basically the same, and in any ways, the sample variances in a purely random population are so low it doesn't matter which you use. But when you have patchiness in your habitat that you wish to sample, and you don't know where those patches are ahead of time, or if organisms tend to cluster in groups, or if you have combinations of patchiness and clustering, in all those instances, a systematic design is much more precise. So you generally get much tighter spread of your sample estimates from 10,000 repeated surveys using the systematic design compared with a random design. So how much better do they perform? Well, one of the best ways to assess that is to ask how many more random transects would you need to equal the precision that was observed with 100 systematic transects. And the answer is that in that first clustered population where you only have patchiness, and for the second, you need either 344 random transects, roughly, to equal 100 systematic transects, or you need 430. Similarly, for where there's only clustering behavior, you need 300 random transects to equal 100 systematic ones, or values of 3 to 5 or almost 6 times as many. So in general, the outcome is that with those populations, you need approximately 3 to 5 times as many random transects to equal the precision of a systematic design. So you would actually have to search 3 to 5 times as much study area to get the same information about population density inside that study region. Now we looked at 30 additional simulated populations in order to see how general these results would apply. These are the same 30 populations shown a little bigger. And we range from very essentially unclustered, totally random, to quite highly clustered populations, but more realistically distributed ones. These are generated using a variogram and a GSTAT package that's available in R. And what you find is that it turns out that the improvement that you achieve with systematic designs is more restricted than we found in the first study. That is to say, and we don't think this has been observed before, which is it turns out that systematic designs are really only better if the sample sizes are larger, which is to say when you're starting to get sampling variances that are reasonable at that point. So larger sample sizes, and systematic is generally only better for these more highly clustered populations in the sense that the range of spatial autocorrelation is broader. That's really the only difference between these rows and these. These rows, we designated that the population density should be, the clusters are roughly about 50 meters across, declining exponentially, 100, 150, and 200. So with this broader range of spatial autocorrelation, that's when systematic is better. So, yeah, well, that's the result. No time to philosophize at this point. Now, if we consider the second question of sample plot, what shapes are better, we find that the answer is more simple. There's no restriction in the outcome. Looking at the red bars being random and blue bars being systematic, when these bars exceed the line at value of 1, it means that the sampling variances of random are bigger than the sampling variances of systematic. So since in essentially every case, for all the populations, all the spreads of range value that affected systematic versus random, they don't alter the outcome for plot shape, which is that in essentially every instance we find that a long, thin transect, in this case it's a 1 by 100 meter transect, compared with a 10 by 10 square quadrat. So you're searching the same area. The long, thin transect does substantially better. In some cases, 2 to 3 times better, 3 to 4 times, or even 5 or 10 times better. If you combine long, thin transects, as you can imagine, with that are systematically allocated, they do much better still than random quadrats. So why use a random survey design? Well, the big advantage of a random design is using our standard formula from the textbook, S squared over n. You can estimate the confidence interval very reliably with a random sample. No matter how complicated the distribution, S squared n will always work if you allocate your samples randomly. So you can better estimate your confidence intervals with random, but they're going to be much wider than if you had used a systematic design. But with a systematic design, it's hard to know how much better your confidence intervals really are because they're difficult to estimate. They involve information about the correlation structure of the population, and that's complicated. So we looked at 13 different variance estimators, again in the same 6 populations. These are from the literature and 3 that we came up with. And focusing on the 5 clustered populations, the normal SE of S squared over n is by far the worst performing in estimating standard error or confidence interval for the systematic design. By the way, I should tell you, if the box lies on the blue line, it means that those estimates of variance are correct. And lately they've been promoting V2 and V3 as being superior, but they're only slightly so, but they still do appallingly badly for most of the populations we tested. And some ecological literature has been using V2 and V3, but we can't recommend them based on the outcome of these tests. But 2 that we do find, V8 and VW, which use the correlation in the simplest possible fashion, in many cases fall right on the blue line. So they really are accurately estimating confidence intervals for these systematic designs in these populations. And what's more, the boxes are much more narrow. So the confidence interval estimates are far more precise than for all the other estimators we tested. So not only are they far more accurate, V8 and VW, but they also are much more precise. And so this stuff is reported in a paper I'll show you at the end. Now, so we answer the 4 questions. Which is more precise, random or systematic? The answer is systematic, but principally when you have reasonably larger sample sizes, 25 or 100, and longer range autocorrelation relative to the geometry of the sampling design. Second, which is better, long, thin transects or square quadrats? The answer is unequivocal and applies for all the designs and populations we tested. Long, thin transects are superior because they're more likely to encounter animals somewhere along the length of the sample. So you have many fewer zeros and many fewer very high values, and more whose average value is close to the true value because you're sampling along a broader range of correlation within the study region. If systematic sampling is more precise, why is it not always used? Well, because we still don't have a fully reliable estimator of confidence interval for systematic samples. And lastly, how can we better estimate confidence intervals? Well, you could do a lot worse than Walter's V8. And I'd like to thank Sarah Gosley, who sent us some code that we used. And this recent paper in Ecological Applications has some of the work that was just presented here. So you can have a look at that if you wish.